Okay, cool. All right, since I just started the recording, I'm gonna start over again. Tonight we're talking about injectors. It's pretty much the last piece of the engine that we haven't discussed yet. So we're just gonna go over the basics of injectors, the different types of injectors, and a little bit on how to design them. So the basic functions of the injector is obviously to inject the fuel and oxidizer into the combustion chamber um, and allow the combustion of uh, the propellants. So the injector needs to make sure that that happens at the correct flow rates of your fuel and oxidizer. And another important thing is that it needs to make sure the propellants are mixed completely, as incomplete mixing will result in uneven combustion. Parts of it will be fuel rich, parts will be fuel lean. You'll get hot spots on the chamber walls that will lead to uneven heating there. You won't get the exact combustion reactants that CEA is giving you, and that's no good. So the injector really needs to make sure that the mixing of the propellants is complete. And the last thing is it needs to make sure that all of the propellants are atomized adequately, which basically means um, when they when the injector injects it into the engine, that the propellants are in as small of droplets as possible. And that's because that allows more surface area on the droplets, um, so that the reaction time will be faster. If you don't have good atomization of your propellants, you'll have a slower burn time, incomplete combustion, and then your CEA will be off again. Um, so yeah, all important things that the injector has to do. All right, so there are a few different types of injectors. Um, there's two main ways that injectors are broken up. So on the left, you have jet type injectors, and on the right, you have pintle type injectors. So within the jet types of injectors, there's a few different ways you can arrange the jets. Basically, the jets are just um, you have like a shower head with a bunch of really tiny holes that all shoot into each other, and that's how the fuel and the oxidizer gets mixed and atomized. So if you see here, you have a bunch of different types of patterns you can use, doublet impinging, which looks like, yeah, you have alternating fuel and oxidizer that will then mix with each other. Um, you have triplet, you have self-impinging, and you just have a normal shower head, I guess. This kind of stuff is complicated. We don't deal with it too much. I think the Methalox engine uses this, and they made the injector as part of their capstone. But as a club, we haven't really touched this. Um, the other type is a pintle type injector. So basically, you have um, fuel and oxidizer are completely separate, and they're manifold into the injector. One of them goes down through a hollow cylinder and comes out of a bunch of holes at the end of that cylinder. The cylinder is called the pintle, and then around the pintle you have another like donut-shaped orifice that the other propellant flows through, which is we just call it the annulus since it's an annular orifice. Um, yeah. Okay. So a little bit more on each type of injector. Um, yeah, so the jets, when they collide with each other, when they impinge on each other, that's what atomizes and mixes the fuel, which means you have to have these jets aligned perfectly. Otherwise, they'll miss each other, and then you won't have your mixing or your atomization. So that's a challenge there, is to get the machining tolerances and manufacturing tolerances to make sure they line up. Um, yeah, the overall machining for uh, showerhead jet type injectors is very difficult. You can either do metal 3D printed, which is what the Methalox capstone did, um, or you can do a series of stacked plates. In the end, it always ends up being fairly complicated. The modeling for a metal 3D printed version, the SolidWorks there is quite complicated. And then for if you're doing a machined stacked plate design, um, you have to worry about all types of like sealing interfaces, and that's just very complicated. Um, Another thing for the jet type is you want to have the resulting momentum of the colliding jets to be axial in the direction of flow down the nozzle. Um, so yeah, you got to do the math to get that right. The one advantage these have are they're very scalable to large engines. You know, it's literally just a pattern of jets, and you can just keep adding them as the injector face gets bigger. I know at least the F1 engine for the Saturn V rocket used um, some type of jet injector, but yeah, they also blow up a lot. I'm not exactly sure why. I think Arun could probably talk more to that once he gets here, but yeah, I think it's just they're very susceptible to, if you don't have the tolerances exactly right, you can get very weird combustion characteristics that will lead to explosions. I know this happened a lot in actually one of the pain points on the F1 engine for the Saturn V that brought us to the moon was the injector. And if you look, you can actually find a lot of videos of tests of that engine blowing up before they were able to get it right. And I don't think they were even able to do any like mathematical math modeling on it or like any kind of analysis. I think they literally just tried things until it stopped blowing up. Um, so yeah, jets are interesting, and I don't like to deal with them. Oh yeah, the other thing is we did deal with it on the Methalox engine, and when we had to get a replacement printed, because that one was I don't know, I think I mentioned that it was metal 3D printed, but when we got it printed, a lot of the jets were clogged because the printer's tolerances weren't high enough. So that was a pain to deal with. But anyway, on to some more about pintles, my personal favorite. Um, so basically, you have a sheet impingement. So you have at the end of the pintle a bunch of jets shooting out in all directions, and then you have the other propellant is flowing straight down around that. So you're always going to have good impingement there, good atomization. Um, when Arun had made the slide, he said that they were easily machinable. I changed to put that in quotes because that really depends. I know on the IPA GOX engine, that one's also uses a pintle, but the holes in their pintle were very small. And Julian, he's one of our alumni who worked on that engine. I think he broke like 10 or 15 drill bits trying to make it. That's probably an exaggeration. I think it was more like 5, but he broke a lot of drill bits and complained a lot about that. Um, so yeah, pintles are more easily machinable than showerhead jet type injectors, but they are still a pain. Um, yeah, again, because the pintle naturally impinges, you don't really need to have as close of tolerance there. Um, yeah, so it uses a recirculation zone to stabilize combustion. If we go back a slide, um, basically, as you have your fuel injecting this way and your oxidizer injecting this way or this way, they mix, and then they'll create recirculation currents here and in the middle of the engine here that will help stabilize combustion. Yeah, they are not. I would kind of disagree with this. They can be scalable. They're not quite as scalable as showerhead jet injectors. But yeah, once you get pretty big, pintles get pretty wide and less efficient, since you have um, all of your propellant is coming out only in like one donut shaped area. Yeah. All right. Let's move on. All right, so now we're going to talk about designing injectors and what that process looks like. This is mostly going to be for a pintle type injector. I'll mention what would be different if you're designing a shower head injector, but for the purposes of this, I think, actually, before we move on, next Tuesday, we're going to have a lecture or a session for you guys to work in your groups. You can work on designing an injector if you want, following this design guide, or you can keep working on whatever you were working on last week. So yeah, but here is just the design process, so you guys know, and in case you want to follow along with it next week. So first thing you would do is pick a reasonable pressure drop across the injector. The rule of thumb is it should be around 10 to 20% of the chamber pressure. And that's so that, well, first of all, so the pressure drop is, so you have the pressure upstream of the injector, and then, as you force it through all of these orifices, it's gonna drop in pressure. So we're just talking about that drop across the injector face. So that should be about 10 to 20% of the chamber pressure, and that will prevent any combustion from flowing back up the injector and exploding in there, in case there's weird pressure combustion stuff in the combustion chamber that make a higher pressure that would flow backwards. So next, if you're doing a pintle, you'll figure out which propellant flows through the pintle and which is going to flow through the annulus. In the end, we're going to try to balance it so that the momentum is facing 45 degrees down, and it's not, favoring the axial direction or outward direction. But general rule of thumb that I've used for regen is the higher mass flow rate goes through the annulus, since that's going down the axis of flow. So I don't know, you just have already higher mass flow rate going that direction, so it's easier and more efficient combustion. So once you figure out which propellant is going through which area, and your pressure drop, we can use the discharge coefficient to find the orifice areas. And the discharge coefficient is a non-dimensional number, which is fake. Non-dimensional numbers are something you'll learn about in fluids. It's basically, I don't really know how to describe it. I'll just talk about what the discharge coefficient is, and you'll kind of get an idea from that. So the discharge coefficient is basically a number that we come up with that has no units, to just relate the flow parameters, like flow rates and properties of the flow, to the pressure drop across an orifice. And it's dependent on the geometry. And so the reason it's a non-dimensional number, so here is the formula for discharge coefficient. Q is volumetric flow rate, CD is the discharge coefficient, A is cross-sectional area. Delta P is the pressure drop across the orifice, and then rho is your fluid density. And then it has the same thing shown here in terms of mass flow rate of propellants. So basically the discharge coefficient, and any non-dimensional number really, is a way that we can describe the relation between two things. In this case, it's flow parameters and pressure drop in a way that is scalable and applicable to other fluids. So that's why you have properties in here, such as the fluid density and stuff. So basically, you can take this CD and it's specific to this geometry. And if you keep the geometry the same and like scale it up, discharge coefficient will be the same. Even if you say are testing with water, but you're actually using LOX, the discharge coefficient will be the same, and you just plug in numbers here to get what the actual pressure drop would be if you're keeping the mass flow constant, or if you want to keep the pressure drop constant, what mass flow you should use. CD, yeah. So CD is the discharge coefficient, and then delta P is the pressure drop across the orifice. So here's like this table shows a bunch of different orifices. So delta P is basically the pressure here on this side of the orifice minus the pressure over here on this side of the orifice. Q, yeah, Q is volumetric flow rate. Thermofluids is weird. You'll learn that between like fluids and heat transfer stuff, they use a lot of cross variables and it gets really confusing. I don't know why Q is volumetric flow rate, but it is. It also represents heat. Yeah, which is confusing, but in this case, it's volumetric flow rate. And Rishi, this is for incompressible flow. If you have compressible flow, don't worry about it. That's more complicated. So yeah. So anyway, here is a table outlining kind of common orifice shapes and stuff, and then it gives some more like dimension stuff, and then the resulting approximate discharge coefficient. So basically, when we're designing, we're gonna start with a reasonable guess based on this table, and then we're gonna have to conduct testing to figure out what the discharge coefficient for us, for our injectors actually is. Since this isn't really something that you can calculate for geometry, you just kind of can measure it and calculate it from measured things. So yeah, so again, so we make a guess, and then we size the orifices. So basically, if you have this equation here with m dot, so you have your propellant mass flow rates. You make an initial guess at a discharge coefficient. You have your fluid density, and you have the pressure drop across the injector that we, why can't I go back? Yeah, the pressure drop that we picked back here, and then you can calculate the total area of the orifice. Also, just to note, for pintle holes, I mean, it kind of varies. I think 0.6 is what we started with regen. After finishing the presentation, I'll take a look and see what it ended up being after testing. Yeah. All right, so once we use this formula and our guess discharge coefficient, um, we're going to divide that up into different holes. So that area that we found using this formula is the total orifice area. So for the holes around the pintle, you're just going to divide it up into a bunch of holes and make sure the sum of the cross-sectional areas of all these holes um, is the area that you calculated from the discharge coefficient. And then for the annulus, this is easier. It's all one big hole. So just the cross-sectional area of this is what we found there. And then as for sizing the pintle, so the diameter should be, whatever it is, should be less than the throat diameter. And that's a good rule of thumb because if the pintle were to break off and it's bigger than the throat diameter, it would fly down and plug the throat and your engine would blow up. So if you make it less than that, if it breaks off, it flies out of the throat, flies out of the engine, and then you just kind of lose combustion and you're all good. I mean, you're not all good, but you're more good than you would have been if the engine blew up. Another thing, I don't know if there's any specific guidelines on how far down the pintle these holes should be. I think we just used that the distance from this plate to the like average or like the middle of the set of holes is the same as the pintle diameter. Um, I don't know if there was any reasoning behind that other than just like, hey, that's a good ratio. But yeah, I don't think it really matters. But I don't know. You can use that. Um, yeah, I guess here is the pencil we made for regen in different stages. I feel like I had. Oh, wait, I skipped the slide. Okay, cool. Uh, I thought I was going crazy there. I was like, why did that slide show up? Okay. So now, after you've made a first pass design, now it's not letting me go back. Yeah, so after you do everything, calculate your areas, put it into this configuration, make a first pass design. Now you get into the iteration and design checking process. So the first thing to look for is called the total momentum ratio. That's what I was talking about earlier, where the momentum of the pintle is at a 45-degree from the axis of the engine. So to find that is relatively simple. So you have the mass flow rates of your of the fuel oxidizer, and then you can also calculate the velocity coming out of the injector using the continuity equation: mass flow rate equals density times cross-sectional area times velocity. Wait, yes. Yes, and that equals rho AV. That V is velocity. Again, fluids likes to use variables weirdly. Sometimes V is volume, sometimes big V is velocity. I don't always know. In this case, yes, that's a velocity. So yeah, once you have the velocity and the mass flow rates for your propellants, um, multiply those together to find the momentum, and just the ratio of those two should be about 1. And if it is 1, that means it's coming out at a 45-degree. The momentum is angled at a 45-degree angle, and that is ideal. Generally, this is what drives the pintle, hole, and annulus sizes. Um, uh, Pressure drop is directly related to the velocity through an orifice. So generally, this is driven by pressure drop. I would say don't worry about that as long as your total momentum ratio is around 1, so like between 0.9 and 1.1, don't worry about making it 1, because that would require different pressure drops for your oxygen and fuel, or oxidizer and fuel. But if you wanted to go crazy and get it really refined, you could go ahead and just make it 1. So then once you make sure that your TMR, total momentum ratio, is around 1, and you have all your orifice sizes and your geometry and everything, you go ahead and run flow sims, and that will give you everything you need to recalculate the discharge coefficient and see whether or not your guess is accurate to the geometry you made. And basically, you kind of keep doing that until everything converges. So basically, you take a discharge coefficient guess, and you calculate your orifice areas based on that, and then you run a flow sim, and based on the results from your flow simulation, you plug everything back in and calculate what the discharge coefficient is there, and then you use that to start over and calculate the areas. So to kind of show that, I'll go back to the equation. So yeah, you start with mass flow, discharge coefficient, pressure drop, and density, and you calculate area. And then once you model that, you do the opposite, where you have area, you have your mass flow, or yeah, you have your area, you have your mass flow, your fluid density, and then the resulting pressure drop from the sim. And then you calculate the discharge coefficient, and then you go back and do that again, where you take the discharge coefficient you just calculated from the flow sim and find a new area. And then you do that all over again until the areas that or the discharge coefficient that you're calculating equals the one that you were plugging in. And it's kind of a pain, but there's no real better way to do that. So yeah. And then after we get that to match and converge, basically are going to actually machine it and do water flow testing to make sure that's the same. And then you have gone through the design process of making a pintle, at least. And then, yes, now we're back on the last slide with everything from the regen engine. Here is Rev 1 of the injector that we manufactured to do water flow testing on. And then here's where the CAD currently stands. We've added a lot of stuff. And this is a very complex pintle. And I think that's about.
Does that with the holes in it in the middle do?
Yes. So I assume you're talking about these holes right here.
Yeah, that one.
Yeah. So another thing is you want to make sure that all of the flow rate gets distributed evenly around the annulus. So basically here, you have, for us, it's our fuel is going through the pintle, and then the oxidizer is coming here. And in order to make sure it gets all the way around evenly instead of just like dumping out of this side, we have this kind of distributor plate that kind of like the flow lands on here, and then it flows around and then goes through these holes, and then into this section of the injector. Which is kind of overkill. I don't think we actually needed it, but we did.
So do the holes in that line up with the pockets below?
Yes.
Don't line up with the flow from the holes above?
Yeah. Oh, okay. Yeah. So these holes, yeah, they line up with the pockets below, and Actually, the only one that the oxidizer is flowing through is this big one here. These are actually bolt holes, so we can attach it to
Gotcha.
stand in the rest of the rocket.
But
So
I'm
yeah,
assuming that like that hole in the back is not coaxial with the distributor plate hole in the back is not directly below the big oxidizer hole.
yep, yeah. This the big oxidizer hole lands like right in the middle there.
Gotcha.
All right, yeah. Any other questions? Feel free to ask them. Um, actually, the plan going forward, as I said, I talked about next week already. You guys can do some injector calcs and stuff if you really want to. Otherwise, keep on working on whatever you were working um, on Tuesday, or it's the Tuesday before Thanksgiving, so you can just go ahead and call your design done. We're not gonna after Thanksgiving. We're not gonna do any more lectures focused on design stuff. Um, I think we're gonna have, I don't know if it's 2 or 3 more. We're gonna focus on a lot of theory that again, you don't need to worry about actually understanding if you don't want to. Otherwise, it's a lot of interesting stuff. But yeah, we're pretty much done with the design aspects of it. And then, as I mentioned, I'm going to work with Arun on getting a 3D printer so that you can all send us a design that you made in CAD and we can 3D print it for everyone. And then next semester, if everyone ends up joining the LRE team, we're going to have you guys work on the test stand that was built for the IPA GOX engine. And fix that up and work on refining one of your designs into an engine that we can actually build and hopefully hot fire by the end of the spring. So yeah, exciting
Is it
stuff.
just normal printing our design, or is that metal printing our design?
Normal printing,
Okay, gotcha.
just to have a little desk toy. So yeah, I guess finished kind of early today, so um, there are not a specified number of positions for next semester. As many people who are interested in doing that can join. I will say though, at some point, we're gonna get to a point where it's gonna be like a too many cooks in the kitchen type thing. We should be able to handle everyone who is in this course, um, and hopefully anyone else who just wants to work on that test stand. But there is gonna be no like hard limit on that. Um, yeah. Yep. So, yeah, as I was saying, we finished kind of early today. If you have any more questions, keep asking me in the chat or a voice. Otherwise, you guys are free to take off.
Thank you.
Thank you.
Have a good one.